We all learned the basics of our solar system: a fiery sun, the rocky inner worlds, and then the giants. But what if everything you were taught about those colossal neighbors, Jupiter, Saturn, Uranus, and Neptune, was just the barest sketch? These aren't just big, swirly marbles floating in the dark. They are worlds of impossible pressure, storms bigger than Earth that never cease, and atmospheres that could turn diamonds into rain. Think about it. Massive systems spinning with such complexity that they almost defy our understanding of planetary formation. We're talking about environments where the rules of physics get stretched, bent, and sometimes rewritten completely. Tonight, we're diving deep past the simple textbook definitions to uncover the shocking truths, the hidden liquid cores, and the truly bizarre physics of the solar system's colossal quartet. If quiet discovery and a fresh, clear look at the cosmos is what you're after, a gentle like and subscribe really helps these conversations reach fellow curious minds. Settle in. It's time to meet the gas and ice giants as they truly are. This vast region of our solar system has been visited by 4 robotic explorers, but when considering the planet Saturn, the success of the Cassini-Huygens mission stands alone. This wasn't merely a flyby. It was an intimate, years-long exploration of a ringed world. The mission's significance is best summarized by the sheer volume of knowledge it produced. The data gathered by Cassini has formed the bedrock for more than 4,000 published scientific research papers. This probe was able to fundamentally rewrite the textbooks on Saturn and its massive collection of moons, discovering at least 6 new natural satellites and providing an unprecedented understanding of their composition and internal structure. Cassini survived a remarkable journey, traveling a total distance of 7 billion kilometers over 20 years. Out of that incredible duration, 13 of those years were spent orbiting Saturn itself, meticulously gathering data on every aspect of the giant planet: its gravity, its colossal magnetosphere, the intricate structure of its rings, and the composition of its atmosphere and interior. The data collection was relentless, continuing right up until the very last moment of the spacecraft's life. Cassini's fate was a deliberate final act, what scientists called the grand finale. It plunged directly into the mustard-colored clouds of Saturn's upper atmosphere, intentionally breaking into thousands of pieces to protect the pristine environments of moons like Enceladus and Titan from terrestrial contamination. This final, dramatic plunge provided scientists with atmospheric readings from a region never before sampled, essentially turning the spacecraft into a 20-year scientific instrument, gathering information until its instruments were crushed and burned by the planet's immense density. The need for such an ambitious mission was established decades earlier. The first probe to successfully reach Saturn was Pioneer 11 in 1979. During that brief flyby, scientists confirmed a crucial fact: Saturn's largest moon, Titan, possessed a thick, dense atmosphere. This discovery immediately changed the scientific agenda. Knowing Titan had an atmosphere and possibly liquid bodies on its surface meant a simple flyby wouldn't be enough. The scientific community recognized they needed to return, but this time with a specialized lander to directly sample Titan's unique environment. Although the Voyager 1 and Voyager 2 probes were already deep into space and en route to Saturn at that point, it was too late to retrofit them with a lander. This necessity led directly to the creation of the Cassini-Huygens mission, Cassini being the main orbiter and Huygens being the dedicated lander for Titan. In October of 1997, the combined spacecraft was launched into space. Getting a spacecraft to Saturn is not a matter of simply aiming and firing a rocket. The journey is an immense feat of celestial mechanics, primarily because the spacecraft must constantly combat the immense gravitational pull of the Sun, which is trying to drag the probe back into the inner solar system. To achieve the necessary speed and trajectory to reach the distant outer solar system, Cassini employed a technique known as gravitational assists, or more commonly, a slingshot effect. This required a rare and critical alignment of planets. Cassini first flew by Venus twice, gathering momentum from the planet's gravity field. It then returned to Earth for a third, high-speed flyby. Earth's gravity provided the final, powerful boost that flung the probe outward toward the realm of the giant planets. The final push came as it swept past Jupiter, gathering the absolute last bit of speed required to settle into Saturn's orbit. This precise orbital alignment of Venus, Earth, and Jupiter, which made such a journey possible, is an event that occurs only once every 600 years. Timing, therefore, was absolutely critical to the mission's success. The second pass by Earth was particularly dramatic. The spacecraft truly scraped by, passing only 1,100 kilometers above Earth's surface at its closest approach. This close call is made even more interesting when considering the technology that powered the spacecraft throughout its journey. Cassini's long-term operations were made possible by 3 RTGs, or radioisotope thermoelectric generators. These power sources work not by splitting atoms, but by using the heat generated by natural radioactive decay to create electricity. The power source was essentially a heart made of about 33 kilograms of radioactive plutonium-238, an extremely long-lived power source. It was the heat from this slow, contained radioactive decay that provided Cassini with all the electrical power it needed, remaining effective even at Saturn's extreme distance from the Sunday. Even as the mission neared its end, the RTGs were still producing around 700 watts of power. The decision to use a substantial amount of radioactive substance on a spacecraft carrying out an Earth flyby introduced a minuscule, yet real, safety hazard. If the initial launch or the later gravitational assist calculations had gone wrong, the spacecraft could have crash-landed onto Earth. While 33 kilograms of plutonium spread out over the entire planet represents a tiny amount, scientists had to consider the absolute worst-case scenario. Localized exposure could potentially have caused as many as 5,000 deaths from cancer. NASA ultimately classified this as an acceptable risk because the chance of the mission failing catastrophically and impacting the Earth was estimated at only 1 in 1 million. RTGs were the only viable choice because at the time of the mission's conception, solar panel technology was not efficient enough to power a spacecraft so far away, where sunlight is only about 1% of the intensity it is near Earth. The RTGs guaranteed Cassini a very long operational life, and theoretically, the power source could be functioning even now. The mission only concluded because the spacecraft eventually ran out of propellant. The critical issue facing the mission was the fact that Cassini eventually ran out of propellant. While the radioisotope thermoelectric generators could have continued powering the electronics for many decades, without fuel, the spacecraft could no longer precisely control its trajectory. This meant the probe could, over time, become a piece of space debris and, due to the laws of orbital mechanics, potentially crash into one of Saturn's pristine, potentially habitable moons, like Enceladus or Titan. To prevent the contamination of these unique worlds with any surviving Earth microbes, a serious biological risk known to scientists and to collect the maximum amount of unprecedented data during its remaining operational time, scientists had to find a way to end the mission safely and scientifically. The scientific objectives of the original Cassini mission were numerous and wide-ranging. They sought to understand the structure and dynamic behavior of Saturn's spectacular ring system, explore Saturn's collection of moons more fully than ever before, measure the nature and scope of the planet's massive magnetosphere, extensively study Saturn's deep atmosphere, and, perhaps most critically, conduct a thorough study of the moon Titan. This intense focus on the moon Titan is precisely where the second part of the mission name, Huygens, comes into play. Huygens was a specialized lander, a separate robotic probe attached to the Cassini orbiter specifically designed to penetrate Titan's dense, hazy clouds and see what lay beneath. The Huygens probe was a remarkable product of the European Space Agency, or ESA, a collaboration between many nations and engineers. The probe itself was a compact vessel, measuring only about 1.3 meters wide and weighing 300 kilograms at the time of its critical separation from the main Cassini orbiter. The separation of the Huygens probe from Cassini took place more than 3 weeks before it entered Titan's atmosphere, leaving the small lander traveling alone for 22 days across the void. During this entire silent transit period, the only system aboard Huygens that remained active was a specialized internal wake-up timer. This timer was meticulously set to bring the probe's complex array of instruments online, just 15 minutes before the vessel plunged into the dense, frozen layers of Titan's atmosphere. This short time frame was calculated to save precious battery life, ensuring maximum power for the scientific work ahead. When the timer did its job and the probe woke up, the data it began immediately collecting was nothing short of astonishing. The descent itself was the primary mission for Huygens, lasting approximately 2.5 hours from the moment it began to experience atmospheric friction until it made contact with the surface. During this descent, the probe acted as a floating, data-gathering laboratory, taking critical, continuous readings of the atmospheric pressure at various altitudes, its exact chemical composition, the speed and direction of the powerful winds, and various other environmental factors. These measurements were vital because Titan's atmosphere, while containing nitrogen like Earth's, is rich in methane and ethane, substances that behave in ways entirely foreign to our own oxygen-rich air. Because the primary goal was to measure the atmosphere during the descent, the chemical battery life of the Huygens probe was not designed to last long after it made its final landing. Scientists at the time were genuinely unsure what Huygens would land on, given the frigid temperatures which sit hundreds of degrees below zero on the Celsius scale and the known chemical makeup of Titan. They had designed the probe to survive a landing on a body of liquid, possibly an ocean or a lake, made not of water, but of liquid methane and ethane. What the probe actually encountered was different. The images and data Huygens transmitted back suggested it had landed not on a vast liquid surface, but on what appeared to be the bed of a dried-up lake, a landscape shaped by fluids that had evaporated or drained away, a place where liquid hydrocarbons once flowed, leaving behind a surface texture resembling damp sand or clay. Even setting aside the profound scientific data collected by both the orbiter and the lander, the Cassini mission itself has been remarkably successful in another, more public way. Over the course of those 13 years in orbit, Cassini was able to provide some of the most stunning and awe-inspiring pictures ever captured in space. The photographic portfolio showcases the breathtaking beauty of Saturn itself, the golden and striped atmosphere, the shimmering and razor-thin rings, and, of course, the distinctive features of its many moons. To truly convey the scope and the dramatic motion of the Cassini mission, dedicated scientists and digital artists undertook an enormous task. They took over 1 million individual photos captured by Cassini and meticulously processed, color-corrected, enhanced, and sequenced them to create cinematic views. These visualizations give viewers the extraordinary sense of what it would be like to actually be sitting aboard the Cassini spacecraft, moving silently through the Saturnian system. It is crucial to note that these are not computer-generated images. There is no CGI involved. They are genuine scientific photographs, simply arranged and presented to convey movement and depth, making the entire journey accessible to everyone. As Cassini's precious fuel began to run critically low, the scientific teams in command shifted their focus. They realized the impending end of the mission was not a failure, but a final, unprecedented opportunity, a chance to get the most scientifically valuable data possible from the time they had left. To achieve this final surge of discovery, they sent commands to the spacecraft, instructing it to perform a series of extremely close flybys of the planet and several of its inner moons, approaching Saturn and its main ring system closer than it ever had before in its lifetime. This spectacular final phase, which commenced officially on November 30th, 2016, involved Cassini repeatedly climbing high above Saturn's North Pole, then executing a steep dive down to a point just outside the narrow F-ring, the outermost boundary of the planet's main rings. The probe completed 20 of these daring orbits. The reason for these 20 close approaches was twofold: to gather close-range data on the F-ring itself, and to fine-tune the spacecraft's trajectory using the slight gravitational pulls of the inner moons, saving the last bits of the now precious fuel. This set the stage for the true climax. On April 22nd, 2017, Cassini performed a great leap, arcing over the main rings to begin its final and most dangerous series of dives. These dives took the probe into the entirely unexplored territory between the inner edge of the rings and the planet's atmosphere. This was the legendary Cassini Grand Finale. This final series of loops and dives progressively brought the probe closer and closer to its gigantic subject of study, confronting ever-increasing danger as the spacecraft encountered denser particle fields and greater gravitational forces. However, this close proximity meant that the data being collected was the purest and most detailed possible, a scientific treasure trove. As the path became more aggressive, Cassini's potential for eventual annihilation became a certainty. The final scientific purpose of this aggressive mission design was clearly stated by the National Aeronautics and Space Administration, or NASA. As the spacecraft plunged through and past Saturn during the grand finale, it collected incredibly rich and valuable information that even the mission's original planners might never have conceived of. For instance, the spacecraft was able to make highly detailed maps of Saturn's powerful gravity and magnetic fields. To measure the gravity field, scientists precisely track the spacecraft's motion using radio signals. Tiny variations in Saturn's mass distribution cause minute changes in Cassini's speed, and by measuring these shifts, scientists can infer what lies deep beneath the clouds. This unique dataset helps reveal how the planet is arranged on the inside, potentially helping to solve the long-standing mystery of how fast the planet's deep interior is rotating a piece of information that is surprisingly difficult to measure from a distance, because Saturn has no solid surface features to track. The grand finale significantly improved the knowledge of the precise amount of material contained within the rings, bringing scientists much closer to understanding their exact origins and age. Cassini's various particle detectors were able to sound and sample tiny icy ring particles that were being funneled directly into the atmosphere by Saturn's powerful magnetic field. Simultaneously, its cameras captured astounding, ultra-close images of both Saturn's rings and the swirling cloud tops. No other mission had ever explored this unique region so close to the planet itself. The deep understanding gained from these final activities will improve the overall knowledge of how giant planets and the families of moons and rings that surround them everywhere in the cosmos initially form and then evolve over billions of years. At the very end of its final orbit, as it began to fall through the atmosphere of Saturn, Cassini completed its 20-year mission by ensuring that the biologically interesting worlds like Enceladus and Titan would never be contaminated by any hardy microbes that may have stowed away and survived the journey from Earth intact. The decision to sacrifice Cassini's long-term survival was an easy one for the mission controllers to make. The spacecraft was already rapidly running out of fuel, which meant its ability to maintain a precise and predictable orbit was already nearing its inevitable end. Because its longevity prospects were gone, NASA became willing to trade the remaining years for an unprecedented chance at extreme closeness to Saturn. This pivotal decision gave Cassini the authorization to approach the planet closer than any machine before it, daringly darting in between the ring system itself, an area that was previously too risky to approach. The unique perspectives captured during this grand finale showed us sights we had never witnessed. By plunging into the territory close to the rings and the planet, Cassini revealed the intimate, complex relationship between Saturn and its collection of small, inner moons, often referred to by scientists as shepherd moons. These tiny moons are not merely orbiting, they are actively managing the entire structure of the vast ring system. Beginning with the moons that shape the A-ring, Cassini provided a breathtaking, close approach to the moon Atlas. This small satellite is approximately 40 kilometers wide and orbits near the outskirts of the A-ring. What makes this moon look so remarkable, almost bizarre, is the striking lack of impact craters across its surface, which appears surprisingly smooth. This unusual feature makes Atlas look less like a moon and more like a flattened, flying disk, sometimes described as a flying saucer. This shape is not a naturally formed sphere, but rather the result of an ongoing process of accretion. The appearance is caused by a constant stream of fine dust particles originating from the surrounding rings, which collect over the moon's surface. This dust settles particularly heavily around the moon's equator, where the rotational and gravitational forces balance in a way that encourages material to accumulate. This continuous settling smooths the terrain and gradually gives the satellite its distinctive disc-like profile, a shape created entirely by the environment it orbits within. A similar dynamic occurs with Pan, which is Saturn's second innermost moon. Pan is smaller than Atlas, measuring about 30 kilometers wide, and is found orbiting within the Encke Gap, a vast, clear division in the main ring system. This gap is roughly 350 kilometers wide. As Pan travels along its path, its gravitational field is just strong enough to nudge and sweep up any stray particles from the rings that attempt to enter its lane. The particles ahead of the moon are slightly slowed and pulled closer to Saturn, while particles behind the moon are slightly accelerated and pushed away. This constant, sweeping action is the fundamental mechanism that keeps the Encke Gap steady and clear, demonstrating the delicate balance of forces in this region. Pan, acting as a small, powerful broom, maintains the vast integrity of the division, against the immense pressure of the billions of ring particles pressing in on either side. Another moon, Daphnis, is one of the smallest known shepherd moons that was studied closely, with a diameter of only 8 kilometers, and it is located within a very narrow division in the A-ring called the Keeler Gap. Though its gravitational force is incredibly weak, the moon is tiny. After all, that weak pull is just enough to affect the nearby ring dust particles as it brushes past its orbital boundaries. The result of Daphnis's subtle gravity is the creation of spectacular waves, or ripples, that move through the ring material. As Daphnis slightly perturbs its orbit, the particles respond with dramatic motion. These ripples are not confined to the flat plane of the rings. The waves move both side to side, horizontally, and up and down, vertically. This vertical movement is highly significant and is clearly visible in the elongated shadows the ripples cast across the flat ring plane when the sun's light hits them at a low angle. The gentle gravitational tug from the moon is sometimes even strong enough to visibly rip material directly out of the ring, creating a small, persistent, trailing wake of debris. Observing this, we are looking at the direct influence of gravity on a massive scale, where an object merely 8 kilometers across can continuously sculpt structures thousands of times its size. Moving beyond the individual moon interactions, Cassini also captured truly spectacular images of the ring dynamics themselves. One of the most revealing images from the grand finale showcases the phenomenon known as the Janus 2-to-1 spiral density wave. At first glance, what is visible in the photograph appears to be many separate, distinct rings. However, this complex structure is actually the result of the same fundamental physical process that creates the beautiful, majestic spiral structure of entire galaxies, though in this case, the arms are wound far more tightly together. What we are seeing are effectively two massive spiral arms that loop around the planet many times over. This means that every second line visible in the image belongs to the same spiral arm, creating an intricate, repeating pattern that stretches for hundreds of thousands of kilometers. This particular image captures a section of the B-ring at a specific location where the ring particles complete exactly 2 full orbits for every 1 orbit completed by Saturn's moon, Janus. This predictable, rhythmic interaction is known as a 2-to-1 orbital resonance. To understand this, imagine a small boat circling a large island. Every time the boat completes exactly 2 full laps, it passes the same spot where a larger vessel representing the moon gives it a tiny, perfectly timed nudge. This constant, rhythmic nudge amplifies the movement of the particles over time, creating a cresting, dense wave that travels through the ring material. The photograph gives the illusion that the image is slightly tilted or warped away at the top left corner, but this is not the case. The illusion is created by the highly complex way these density waves propagate or travel outwards from the planet. As the wave moves further away from the point of orbital resonance with the moon, the distance between the peaks of the waves, known as the wavelength, gradually decreases. This reduction in wavelength is a subtle but profound visual demonstration of how energy and motion travel through the billions of ring particles, dissipating as they move away from the source of the force. This resonance mechanism becomes even more mind-blowing when we consider the behavior of the moon that contributes to it. Janus does not orbit Saturn alone. It shares a complex orbital path with its close neighbor moon, Epimetheus. Every 4 years, these 2 moons perform a remarkable gravitational dance, swapping orbital positions with each other. This exchange of location takes place without a collision because the difference in their original orbits is minimal. Every time this gravitational switch takes place, the rings immediately respond by creating a new crest or peak in the density waves. NASA scientists determined that the distance between any successive pair of these wave crests corresponds precisely to 4 years of the wave propagating or moving downstream from the resonance zone. This means that the wave pattern visible in the rings literally encodes decades worth of the specific orbital history of both Janus and Epimetheus. It is a natural archival record written in the ice and dust of the ring material. According to this interpretation, the segment of the wave located at the very upper left of this stunning image corresponds to the orbital positions of Janus and Epimetheus around the time of the Voyager flybys in 1980 and 1981. That period was, significantly, the time at which Janus and Epimetheus were first confirmed by scientists to be 2 distinct objects, rather than one blurry body that had been temporarily separated. The ring structure, therefore, acts like an ongoing physical memory of the solar system's mechanical past, recording the gravitational events of the giant planet system. Apart from other beautiful and detailed images of the rings, other interesting sightings have been these small propeller features dotted around the rings in a number of locations. They are named propellers because they consist of a small, unseen central object, a moonlet that creates a 2-bladed disturbance in the ring particles around it, resembling the propeller of an airplane. This image shows both sides of the rings. The top image shows the illuminated side, the one lit directly by the sun, and the bottom image shows the unlit side. Scientists do this to compare and try to figure out details of the ring's structure. The illuminated side shows how the light reflects off the dense ice particles, while the unlit or dark side is better for spotting fine, powdery dust and vertical structures, which are often invisible in the bright glare of the sunlit side. Even though the scale of this image is only about 500 meters per pixel, the moonlet at the center of the propeller might not even be able to be resolved, meaning it is too small to be seen clearly. You might just be able to see some trace of it in this top image, but what can be seen is that the moonlet is physically connected to the rings by this band of materials. The physics at play here involves the moonlet's tiny gravitational pull. It pulls on the ring particles in front of it, slowing them down and causing them to drop into lower, faster orbits. At the same time, it pulls on the particles behind it, speeding them up and flinging them into higher, slower orbits. This dual action of pulling and pushing is what carves out the distinctive propeller-shaped gap. This was not the only moonlet found trying to create a gap in the rings. Here is another, found right next to the Anchor Gap. And here is another, which is probably the biggest out of all 3. None of these moonlets are thought to be bigger than 2 kilometers in diameter, and they probably have the density of a snowball. This snowball density implies they are not solid rock, but rather porous, icy conglomerates, which gives scientists clues about how moons might begin to form within a ring system. The last interesting thing Cassini was able to image within the rings is extremely small but solid objects which are formed around the E-ring. The E-ring is the vast, tenuous cloud of ice particles sprayed into space by the geysers of the moon Enceladus. These objects are potentially caused by the gravitational perturbations, or disturbances, of some of the shepherd moons in that region. They seem to be solid, or at least much denser than the E-ring's powdery ice, because they have survived crashing into the E-ring a number of times. As they plow through this icy fog, they kick out dust and particles, which sometimes then even follow their orbit, as can be seen by the haze around them. The objects themselves are not actually visible, as they are completely obscured by the dust they are kicking up. As Saturn's northern hemisphere was in full summer at the time, Cassini flew by. Its remarkable hexagon around the pole was in full view. This is not a solid structure, but rather a persistent, high-speed jet stream, a river of air that has locked itself into a stable, six-sided weather pattern. In the center of the hexagon is found a permanent polar vortex, which is essentially the eye wall of a massive, long-lived hurricane, larger than the Earth itself. Interestingly, the pole seems to be changing color with the season. You can see this quite clearly in comparison to the year 2012, when the pole appeared quite dark, almost blue, in color. With the northern hemisphere in full summer, it was receiving constant, direct sunlight. This increased solar radiation was driving photochemical reactions in the upper atmosphere, creating a thicker haze of complex particles. This photochemical smog is what caused the pole to change from its winter blue to a golden, yellowish color. With the assistance of other wavelengths of light beyond what the human eye can see, other storms are visible and could be seen dotted all over the planet, as well as atmospheric bands reminiscent of Jupiter, just not quite so vivid in natural light because they are buried deeper beneath Saturn's upper haze. Also, because of the proximity of Cassini to the planet during its final orbits, it was able to get a good look at the planet's horizon. On the left of the image can be seen a haze in the stratosphere, a high layer of the atmosphere. This haze then disappears towards the right of the image. When Cassini did enter the atmosphere on its final approach, it was thought it would not survive to even reach this haze. However, scientists were not too worried about that. What was of particular interest to scientists is what the atmosphere consists of. Cassini would dive into that atmosphere to find that information and would burn up in the process, making these the last readings that Cassini would ever send. But 1 week before it entered the atmosphere, Cassini was still taking images. Some of these final images are fantastic, although be aware that Cassini is not capable of real-time video capture. The videos I am about to show you are time lapses, the splicing together of countless individual images into glorious visualizations of what it would be like to fly with Cassini on its ultimate journey into Saturn. Not all of these images are of Saturn itself. The first time-lapse we will look at is from the 8th of September, 2017, only 1 week before the end of Cassini's mission. One of the main focuses of Cassini during its mission was the moon Enceladus, one of the prime candidates in the solar system to contain life in a subsurface ocean. Cassini discovered over 100 water plumes erupting through the moon's icy crust from this ocean. This water freezes in the space environment and has now formed the beautiful E-ring around Saturn. This ring is very tenuous, so thin that it is only visible when backlit by the sun, and it is potentially the bluest naturally occurring object in the solar system, as its fine ice particles scatter blue light most effectively. Here is a great view of Enceladus's effect on the densest part of the E-ring. You can see the plumes, the source of the ring, simultaneously disturbing and replenishing the ring material. Cassini's final look at Enceladus's plumes was captured in this remarkable time-lapse, taken over a 14-hour period. On the 11th of September, Cassini was near the furthest point of its final orbit and captured this beautiful mosaic in natural light. Visible are the thickest of Saturn's rings, D, C, B, A, and F, with Saturn's short shadow being cast over them. Saturn's northern hemisphere was experiencing summer during this time, which means that Saturn's most famous hexagon storm is visible in all its glory. You can also just about notice Saturn's subtle bands in natural light. What's really interesting about this image, however, is that the night side of Saturn is dimly illuminated. This is not light from the planet itself. It is due to light reflecting off the rings. The bright, icy rings act like a giant, shattered mirror, catching sunlight and casting it down onto the planet's dark side. This ring shine means Saturn's nights in the hemisphere facing the sun do not get that dark. Below the glow of the rings, Saturn is pitch black. As Cassini began to approach Saturn again on the 12th of September, it took images of Saturn's atmosphere near the planet's terminator line, the line between day and night. Incredibly, because the sun is so low in the sky here, huge cloud structures can be seen casting shadows that stretch for many kilometers. By measuring the length of these shadows, scientists can calculate the precise altitude of these clouds, giving a three-dimensional structure to the atmosphere. You may think this is a close-up of Saturn, but we are looking at a scene about 5,500 kilometers across. Saturn's moon Titan could easily fit in this shot. Cassini was getting closer and closer to Saturn. On the 13th of September, it appeared one last time at Daphnis, the tiny moon in the Keeler Gap. Some of you keen observers will notice ripples in front of the moon as well as behind it. This is due to the orbital speeds of the rings in the moon. The inner ring orbits faster than Daphnis. Its particles approach the moon from behind, get pulled by its gravity, creating a ripple, and then speed past it. On the other hand, the outer ring travels slower than Daphnis. The moon overtakes these particles, pulling on them as it passes and leaving a ripple behind. By the time the ring material on either side reaches Daphnis again, the ripples have already smoothed out. On the same day, Cassini had one last look around the Saturn system. It captured a view of Titan, a moon it focused on heavily during its mission, a remarkable world with a thick nitrogen atmosphere. It also peered at Saturn's rings, with the uneven F-ring just about visible at the bottom of the image. And as Saturn got bigger, it took one last look at Enceladus over a 40-minute period, watching it before it disappeared from view behind the limb of Saturn. The final image Cassini ever took was looking over the region where it would plunge into the atmosphere. It was nighttime here, and so Saturn is lit up by light reflected off the rings. On the final day, photos were not on the scientists' agenda. As beautiful as they are, they use up a lot of valuable data bandwidth. Scientists wanted to get every bit of scientific data in real time before the spacecraft was destroyed. This was a unique opportunity. We had never probed Saturn's atmosphere directly before this. When Cassini first hit the tenuous upper parts of Saturn's atmosphere, it was traveling at 123,000 kilometers per hour. At this speed, even the thinnest gas behaves like a solid wall, generating immense friction and heat. The remnants of Cassini's fuel were deployed by its thrusters, not to slow down, but to fight the atmospheric drag and keep Cassini's large, dish-shaped antenna aimed precisely at Earth. At this point, Cassini was 1,900 kilometers above Saturn's visible clouds. A minute later, these thrusters were firing at 100% capacity, fighting desperately to keep Cassini from spinning out of control as the atmosphere grew thicker. Cassini was directly sampling Saturn's atmosphere, sending back data on its composition, but this atmosphere was also heating the spacecraft to extreme temperatures. Just 10 seconds later, the thrusters were overcome. The atmospheric force was too great. Cassini began to tumble, and the stream of data, the antenna no longer pointed at Earth, was cut off. Cassini's onboard computers at this point would have been trying to figure out what was going wrong. Its gyroscopes and star trackers would tell the computer that it was spinning, and it would likely have gone into a safe mode to divert all power in a futile attempt to right itself. A minute or so later, the spacecraft, now superheated by friction, would have disintegrated altogether and burned up in Saturn's atmosphere. As the final stream of data from Cassini's plunge arrived on Earth, approximately 1.5 hours after the spacecraft itself had disintegrated, this last part of the mission was deemed a profound success. Cassini recorded data from a direct analysis of Saturn's atmosphere, its ionosphere, the dust particles suspended within the atmosphere, and measurements of its magnetic field, and perhaps more information that has yet to be uncovered from the data. That is the truly amazing thing about the Cassini mission. It just keeps on giving. More than 7 years after its final transmission, scientific papers and new discoveries are still being made, as the massive archive of data it collected is analyzed and re-examined with new techniques. What have we discovered from Cassini's data in the years since its groundbreaking mission? You are about to find out, but be aware, some of the things Cassini has learned about Saturn have only served to make the planet even stranger. You may think you know Saturn. Its iconic rings are the largest and most spectacular in the solar system, and its hazy, butter yellow surface is both enigmatic and instantly recognizable. It is the second largest planet, the least dense planet famously. It would float in a large enough body of water, and the 6th planet from the Sunday. And yet, Saturn is an enigma. There is a vast mystery lurking beneath its obscuring atmosphere. A mystery uncovered by the Cassini probe, one that the scientific community still does not have a consensus about. Saturn behaves in ways that our conventional models of physics claim should be impossible, from its internal temperature to its magnetosphere, to even the very length of its days. What is going on with Saturn, and what are our best attempts at explaining these baffling phenomena? The Cassini probe arrived at the gas giant on the 1st of July, 2004. It was not the first probe to arrive at Saturn. 3 others, including Pioneer and the Voyager probes, had already done flybys. However, Cassini's mission was the most thorough. As we have already mentioned, it spent 13 years circling the planet, collecting vast reams of data using its various spectrometers, magnetometers, and other advanced equipment. The knowledge it gave us has been a huge benefit, but sometimes it only serves to deepen Saturn's mysteries. Take, for example, that hexagon storm on Saturn's North Pole. The edges of this 29,000-kilometer-wide storm, a geometric shape forged from a high-speed jet stream, are so vast that the Earth could fit comfortably inside each of its 6 sides. As best as we are able to tell, this storm does not shift its longitude. It remains fixed at its location, traveling perfectly with the rotation of the planet, unlike the rest of Saturn's swirling clouds, which are pushed along by winds that can reach up to 1,800 kilometers per hour. The storm is undeniably a strange one. Scientists do not yet have a full explanation for it, although there are some laboratory experiments on Earth that have created close approximations to hexagons in spinning fluids, but only on much smaller scales. And this storm is not alone. As the mountains of Cassini data started getting analyzed in the years since the end of its mission, more mysteries have started coming in. It started with a fairly innocuous question: how long is a day on Saturn? Although we have watched Saturn in our sky for thousands of years, scientists did not yet have a definitive answer. After all, it was not as simple as looking up at the planet and seeing how long it took for its rocky core to rotate. Saturn's thick, opaque cloud cover obscures any landmarks that might exist on any hard surface far below. Furthermore, those clouds move at different speeds than the core, all driven by the powerful winds. The rings themselves orbit Saturn at many different speeds, so they do not settle this question either. You cannot look at how fast they orbit and hope it is the same as the planet's rotation. After all, most moons do not orbit at the same speed as their planet spins, and rings are no different. Rather cleverly, scientists do have techniques for figuring out the rotation of a gas giant by looking at its magnetic field. It was hoped that this method might be used on Saturn. Planets with magnetic fields, like Earth, are thought to produce them via a dynamo effect. As the planet rotates, liquid metal in the core, in Earth's case, liquid iron, in Saturn's, liquid metallic hydrogen, spins and shifts. This colossal motion of conductive material creates massive currents of energy, which in turn produce magnetic fields. One key feature of this process is that, thanks to this rotation, the pole of this magnetic field is always off or tilted from the axis of rotation for the planet itself. If the two lined up perfectly, the magnetic field, according to dynamo theory, wouldn't survive for long. So, all you have to do is detect the magnetic fields around a planet, which Cassini could do, and watch as the magnetic pole shifts in a circle around the true rotational axis of the planet. Once the magnetic pole has completed one full rotation, you have your day. Only, Saturn apparently does not play by these rules. Cassini discovered that its magnetic pole is almost perfectly aligned with its axis of rotation to an order of accuracy of less than 0.1 degrees. This is a shocking discovery, and in spite of dynamo theory claiming that this should be impossible, Saturn's magnetic field is alive and well. Its magnetic moment is 580 times more powerful than Earth's and is extremely influential on the Saturn system as a whole. Scientists do not know how this magnetic field occurs, as it seems impossible under the standard dynamo theory. Yet, no other method for producing such a powerful field is proven either. Either a planetary dynamo is at play in Saturn's core, but some other unknown effect is occurring in the atmosphere to warp the magnetic field lines to be perfectly aligned with the axis of rotation, or we are observing a completely new method of producing a magnetic field on Saturn. So, it was back to the drawing board for solving a Saturnian day. Fortunately, radiation proved to be of more help. Saturn is an electrically live system. Charged ions move between the layers in its atmosphere, and even between its rings and its ionosphere. Scientists noticed that Saturn emitted radio waves as a result of all the magnetic fields at play, and these radio waves rose and fell in intensity. In fact, it seemed to mirror what you might expect to see as a result of the planet rotating. Higher levels of radiation would appear every 11 hours or so. As a result, scientists concluded with some certainty that this was Saturn's day length. Their initial estimate, based on data from the Voyager flybys, was 10 hours, 39 minutes, and 23 seconds. It was hoped that Cassini would be able to improve the accuracy of this figure. Initially, Cassini was able to do so, but then it got really weird. Over the course of the 13 years of Cassini's study of Saturn, this number started to shift. It drifted by about 1% over the course of a year, sometimes rising, sometimes falling. This almost seemed to imply that the planet itself was altering the speed of its rotation, sometimes speeding up and sometimes slowing down. To be clear, a planet as massive as Saturn should not be doing that. the laws of physics would require an impossibly large external force to make such a change. As such, scientists concluded that this was not happening, and some effect must be, once again, muddying the waters around Saturn. Some aspect of the atmosphere was causing shifts in the fields, making the radiation fluctuate over time, hiding the true, constant rotation of the planet beneath a cloaking shimmer. Another key consequence of the planet's magnetic field is the auroras that shine at Saturn's poles. But while on Earth, our auroras are the result of the solar wind interacting with our atmosphere, it is thought that this does not account for the auroras on Saturn. Cassini detected that at least some of them occurred regardless of what the solar wind was doing at the time, meaning that Saturn's auroras are non-solar in origin. Something strange must be going on inside Saturn. It was also hotter than it ought to be. Saturn radiates out into space about twice as much heat as it receives from the Sunday. While some of this may just be heat left over from its formation or from the gravitational compression of the planet, the rest needed some other way to account for it. Ultimately, all of this needed some unifying explanation. Fascinatingly, thanks to Cassini's data, we discovered the key to all of it may lie within Saturn's gaseous atmosphere. Saturn is a gas giant. It is almost entirely made of hydrogen and helium. Not all of this is gas, as the great mass of Saturn means that the deeper into its atmosphere you go, the more intense the heat and pressure that you are subjected to. It is thought that this pressure forces gaseous hydrogen to become that liquid metal we spoke of. But some scientists theorize that this liquid hydrogen, or perhaps even hydrogen, compressed so densely that it becomes diamond, rains down into the depths of Saturn. The friction this diamond rain generates as it falls through the denser layers below might explain some of Saturn's unusual heat. The rest of the heat comes from the auroras. Although these are not fully understood, it is thought that they are the product of electrically charged particles coming into Saturn from its rings and moons. Whatever their source, these auroras may be creating enough heat to warm the upper atmosphere of the planet. Temperatures so hot create other effects. Where warm fronts meet cold, powerful winds are formed. It is theorized that these winds carry charged ions around Saturn's upper atmosphere, and it is these electrically charged winds that are skewing the data from Saturn's radiation, causing its variance. Perhaps such motion of electrical currents might also explain why Saturn's magnetic fields are not where they are supposed to be. This could be caused by a conductive layer within Saturn's clouds, moving at a different speed than the others, creating fields of their own. At least, so goes the explanation. In all of this, it should be clear that many of these answers lack final proof. The profound mysteries of the impossible magnetic field, the source of the planet's excess internal heat, and the precise nature of the atmospheric winds that cloak the true rotation all remain open questions. The scientific community is still meticulously trawling through the vast, complex data archive provided by the Cassini mission, hoping for further insights. This process is slow, as the data is compressed and encoded, requiring new models and algorithms to properly interpret. But if these insights are not forthcoming from the existing data, then ultimately, it will take another dedicated mission to Saturn, one designed with these specific questions in mind, to find the answers. But what about the length of Saturn's day? Thankfully, this one specific mystery does have an answer, and it turned out the clue lay in the rings after all. Rather than investigate the confusing electrical and magnetic effects of Saturn, which were hopelessly clouded by the unpredictable interference from the upper atmosphere, scientists realized they could look at a more fundamental, reliable force, gravity. They realized that Saturn would also tug on its rings through its gravity. This is fairly obvious, but what was more insightful was that Saturn would not and could not target them uniformly. Saturn is not a perfectly round, solid ball. It is a rapidly spinning giant made of gas and liquid, which bulges significantly at its equator. Deep within its cloudy depths, its core and liquid layers are not perfectly smooth. Any variance in its shape or internal structure, any lumpiness deep inside, results in tiny variances in its gravitational field. The rings of Saturn, a vast, flat disk made of billions of individual ice particles, provided a perfect, enormous, and incredibly sensitive canvas to look for such variance. Scientists theorized that as the planet's uneven internal mass spins, it would create tiny, rhythmic, gravitational pulses. You can imagine the planet's interior as a slightly out-of-shape bell. As it spins, it doesn't ring with a single pure tone. It sends out slightly uneven vibrations. But instead of sound, these are vibrations in gravity. These gravity waves travel outward from the planet's core. At specific locations in the rings, these pulses would pluck the ring particles, causing them to bunch up and create measurable ripples. This is a concept sometimes called ring seismology, using the rings to detect the vibrations and structure of the planet's core, much like a seismograph on Earth detects earthquakes. Scientists started looking for these specific ripples, and by locating them and measuring the precise distance between them, it was finally possible to calculate the true, underlying rotation speed of the planet's core, the source of the vibration. They were not far off from the original radio estimates, but the precision was key. The day was calculated to be 10 hours, 33 minutes, and 38 seconds. And this time, scientists are fairly certain that they have got it right. This measurement is based on the fundamental, unchanging physics of gravity, not the noisy and shifting radiation from the upper atmosphere. So, at least this one deep mystery was solved. And yet, Saturn's other mysteries, the impossible magnetic field, the source of its excess heat, still persist. The next major mission to the Saturnian system will launch in the year 2027. This is NASA's Dragonfly mission. However, this mission will not be studying Saturn itself. It will focus almost entirely on exploring Titan, Saturn's largest moon. Titan is, in many ways, the most Earth-like object in the entire solar system. It is the only place other than Earth that is thought to have a thick, dense atmosphere filled primarily with nitrogen, similar to ours, albeit with no oxygen. It is a world with weather, with rain cycles, and with vast, stable bodies of liquid on its surface, rivers, lakes, and seas. However, these are not filled with water. The temperature on Titan is far too cold for liquid water. Instead, these lakes and rivers are filled with liquid methane and ethane, which behave on Titan just as water does on Earth. It is a cold, alien world, but one that may hold the very clues to how life itself begins. Scientists see Titan as a prebiotic chemistry lab, a place where complex organic molecules are constantly being created, but where the process is frozen, literally, at the stage just before life emerges. The Dragonfly mission will send a large, car-sized drone, a quadcopter, to this moon. It will be able to fly from one location to another, landing to take samples and study the chemistry of this unique environment. So, it is understandable why scientists want to give it a close look. Still, this focus means that it may be some time perhaps many decades before Saturn's deepest internal mysteries find themselves answered. The Saturnian system is a place of delicate balance. The planet's winds, which might prove to be the lifeblood of the system, thrum and flow across its atmosphere. Its delicate balance of magnetic fields and gravity interacts with its rings, keeping them perfectly and precisely aligned. But perhaps the most profound discovery from Cassini is that this alignment, this entire glorious ring system, is surprisingly young. Saturn, the planet, may be over 4 billion years old, but there is mounting evidence that the rings themselves may have only formed in the last 100 million years, a cosmic blink of an eye. Scientists now theorize that a large, icy moon, perhaps the size of Iapetus, strayed too close to Saturn and was torn apart by its immense tidal gravity. The debris from that destroyed moon then spread out into the system we see today, and, just as they were formed, they are now slowly draining away. Cassini's instruments were able to detect this ring rain, a constant infall of ice particles and water vapor being pulled from the inner rings by the planet's magnetic field and gravity. This rain is dumping tons of material into Saturn's upper atmosphere every second. By calculating this rate of loss, scientists determined that in another 100 million years, the rings may be gone entirely. This context adds a profound perspective to our observations. It implies that humanity has arrived at a very specific and fortunate moment in the solar system's history. We are witness to this enigmatic and wondrous world during the brief epoch when it is at its most beautiful. If intelligent life had evolved on Earth just a few 100 million years earlier, or if it evolves a few 100 million years in the future, they might look up at Saturn and see a much plainer, less inspiring planet, perhaps with no rings at all. Capturing the data, the beauty, the scale, and the profound scientific questions of this system just would not have been possible if it had not been for the incredible Cassini-Huygens mission. This truly was one of the greatest space missions of our time. Jupiter is a place of colossal storms, deadly radiation, and captivating beauty. It is a powerhouse whose mass is so great it influences even the Sun itself. This planet is fast becoming one of the most studied objects in our solar system, having been visited by 7 successful flybys, 2 orbiters with 1, the Juno spacecraft, still in operation today, and 2 additional missions planned for the future. There is still so much to know about the 5th planet from the Sunday. What causes its distinctive red and orange coloration? Scientists believe it is a complex chemical reaction involving sulfur, phosphorus, and other compounds. But the exact process, driven by sunlight and massive lightning strikes, is still debated. What is it truly made of? We know it is primarily hydrogen and helium, the same basic ingredients as the Sun, but its deep core remains a puzzle. What lies beneath its obscuring clouds? The current Juno orbiter is trying to answer this very question, mapping the planet's gravity to see if there is a solid core or just a fuzzy, diffuse soup of heavy elements. And what is the nature of its great red spot? We know it is an anticyclonic storm, wider than the planet Earth, that has raged for at least 150 years, but we do not know why it has lasted so long, or what powers it from deep below. Jupiter holds a vital role in the solar system, and it is time to delve into its mysteries. Jupiter is found on the outskirts of the asteroid belt, sitting in the vast space between the orbits of Mars and Saturn. It is, on average, 778 million kilometers away from the Sunday. This distance is often measured as 5.2 astronomical units, meaning it is 5.2 times farther from the Sun than the Earth is. Because of this vast distance, it completes one orbit every 12 Earth years. The axial tilt of the planet is remarkably small, only 3 degrees. This lack of tilt means the planet does not experience significant changes in seasons, unlike Earth or Mars, which have dramatic seasonal shifts due to their tilts. Earth's is 23.5 degrees. Jupiter receives almost the same amount of sunlight on its northern and southern hemispheres all year round. And, very much like Saturn, it spins so rapidly that its radius at the equator is greater than at its poles. It bulges out in the middle. It is a massive planet, the largest in our solar system. Its mass is about 1,000th that of our Sunday. That might not seem like a lot, but one must realize that the Sun contains 99.86% of all the mass in the entire solar system. This means Jupiter's mass equals almost all of the remainder. To put it another way, Jupiter's mass is 2.5 times that of all the other planets in the solar system combined. This immense mass brings about an interesting phenomenon, the barycenter between Jupiter and the Sunday. When we think of an object orbiting another, like the International Space Station orbiting Earth, or even Mercury orbiting the Sun, we do not necessarily think that the smaller object has a gravitational influence on the bigger one. That is because most of the time, the effect is negligible. A barycenter is the center of mass between these two orbiting objects. It is the specific location in space that they both orbit around. For a small object like Earth orbiting the massive Sun, that barycenter is deep inside the Sun. So we just say the Earth orbits the Sunday. But with Jupiter, its mass and distance are far from negligible. The center of mass between Jupiter and the Sun is actually above the surface of the Sun, located at 1.068 solar radii from the Sun's center. This means that as Jupiter swings around the Sun, both of them do a little dance around this empty point in space. The Sun is not stationary. Jupiter's gravity forces the Sun to wobble. This wobble is the exact mechanism scientists use to find large, Jupiter-like planets orbiting other stars. While Jupiter has the greatest mass of any planet, it is not the densest. It is the most massive, simply because it is the largest. Density is about how much material is packed into a specific space. If the planet Neptune, which is denser, were the same physical size as Jupiter, Neptune would actually be the more massive planet. And conversely, if Jupiter were shrunk down to the same size as Earth, our rocky Earth would be over 4 times more massive, because rock and iron are packed far more tightly than the hydrogen and helium that make up Jupiter. As it is, the diameter of Jupiter is 11 times that of Earth, and its total mass is 318 times more than Earth's. As we know, mass directly affects gravity. This means that Jupiter has a huge gravitational pull, measuring over 2.5 times that of Earth, at its cloud top specifically 2.528 g. The gravity of Jupiter is so influential in the solar system that it affects every planet to one degree or another. Its gravity is strong enough to tear asteroids apart and to have captured a massive family of at least 95 known moons. Some scientists theorize that Jupiter destroyed many celestial objects in the ancient past. Its gravitational stirring likely prevented other planets from forming in the region of the asteroid belt. The asteroid Vesta, for example, might have been on its way to becoming a full planet before Jupiter's influence scattered the material in that region. This influence continues today. Scientists even predict that the gravity of Jupiter is so significant that it is perturbing Mercury's already eccentric orbit. enough that in a few billion years, the tiny planet may either crash into the Sun or be ejected from the solar system altogether. At the moment, though, Jupiter could be seen as the hero of the 4 inner planets. Without Jupiter acting as a cosmic vacuum, our solar system would be a much more dangerous place. It constantly sweeps up dangerous objects like long-period comets and asteroids. Its gravity either pulls them in, where they crash harmlessly into its thick atmosphere, or it slingshots them. It perturbs their orbits enough to give them a little kick of energy so that they leave the solar system altogether, never to threaten the inner planets like Earth. Jupiter is, in essence, our solar system's great protector. Even with its great distance, Jupiter can be the 3rd brightest object in the night sky, surpassed only by the Moon and Venus. It shines with a maximum magnitude of -2.94. This brightness scale is inverse, so a negative number is extremely bright. At its peak, Jupiter is so brilliant that it can actually cast faint shadows on Earth. As a result of it being so obvious in the sky, it makes a very nice target for amateur astronomers. As consumer telescopes have improved in recent years, it is amazing what details you can see from your own back garden, including the distinct bands and even the 4 largest moons, which appear as tiny pinpricks of light flanking the planet. But what makes these famous patterns? The visible cloud layer is only about 50 kilometers thick, or 31 miles, and contains ammonia crystals, much like on Saturn. But the vibrant coloration comes from compounds heating up from deep within Jupiter's interior and then rising to the surface. These compounds are known as chromophores. When these colorful chemicals reach the cloud tops, they interact with the ultraviolet light of the sun, which triggers chemical reactions that create these spectacular multicolored bands. The lighter colored bands are called zones, and they are areas of rising gas ammonia ice crystals forming at the top make them appear white. The darker colored bands are called belts, and they are areas of sinking gas where the air is clearer, allowing us to see the more colorful chromophores lurking at lower, warmer altitudes. This is quite the cycle, and the face of Jupiter can change dramatically over time. Even if their colors do change, the actual latitude of these bands remains consistent enough to be given identifying designations, but they can vary in width over the course of time. A great deal of storms and turbulence occur where these bands meet, where gases moving at different speeds shear against each other. It is this high-speed shear that is the reason and the engine behind Jupiter's very famous Great Red Spot. This storm is huge. It can easily fit the entire diameter of the planet Earth within it. It has existed for as long as we have had telescopes powerful enough to resolve it. Since it was first discovered in the 17th century, it might very well be a permanent feature of the planet. Interestingly, however, it has decreased in size since observations began. In the late 1800s, it was estimated to be over 40,000 kilometers wide. Today, it is less than 16,000 kilometers across. Scientists do not know if this shrinking is a sign of the storm dying or just a natural part of its long-term cycle. The reason for its distinct reddish color is unknown, and the color of the spot can vary greatly, from a deep brick red to almost white. The most recent theory for its color is that the storm is so powerful, it dredges up those chromophore chemical compounds from deep within the planet. The storm is also much higher up in the atmosphere than the surrounding clouds, and as a result, it can interact with the sun's ultraviolet light a lot more. This intense radiation breaks the compounds apart, creating the deep red color. This would explain why its color can be much stronger than anything else around it. But Jupiter does not just have one scientifically interesting storm. Another storm, known as Red Spot Junior, or officially Oval BA, formed when 3 smaller white storms merged into one between the years of 1998 and 2000. It has so far passed unscathed by its bigger neighbor and is now quite a prominent feature of the planet. It could last for another couple of hundred years if it avoids the same fate of a similar storm which passed right through the heart of the Great Red Spot and was completely absorbed. So what do we think Jupiter is made of? Well, much like Saturn, under the visible atmosphere are gaseous, then liquid, and then metallic forms of hydrogen. The further into the planet you go, the greater the pressure becomes. Under this immense pressure, hydrogen, normally a clear gas, acts as a metal, conducting electricity. Beneath that deep layer of metallic hydrogen is an ice or a rocky core. Because we cannot recreate on Earth the immense pressures Jupiter experiences, we do not really know what properties these materials have at the core. By volume, roughly 90% of Jupiter is thought to be hydrogen and 10% helium, with trace amounts of methane, ammonia, and others. Jupiter rotates very fast, faster than any other planet, completing a full rotation in only about 10 hours. But, due to it not being a solid body, it does not rotate at the same speed all over. A rotation at the poles actually takes about 5 minutes longer than at the equator. A common question is why Jupiter is not a star, considering it is so massive and is predominantly made of flammable hydrogen. The sad news is that stars do not really work that way. First, there is barely any oxygen on Jupiter to allow for combustion, which is a chemical reaction. Stars produce their heat from nuclear fusion, a nuclear reaction caused by the extreme pressures and temperatures found at the star's core. Current thinking is that Jupiter would need to be roughly 75 times more massive than it is now to have enough gravity to ignite nuclear fusion and become a star. Interestingly though, its physical volume is not too far off from the smallest known red dwarf stars. If you added more mass to Jupiter, it would actually get smaller as the increased gravity compressed it further. And yes, you may have noticed in some pictures, Jupiter does indeed have rings. They are nothing on the scale of Saturn's, but there are 4 known planetary rings, composed mostly of dark dust particles. The main ring is very thin but also very bright, at least in comparison to the others. The rest are quite wide but exceptionally faint. The main ring is about 6,000 kilometers wide, and the only distinctive feature you will see is what is known as the Metty notch. Something else to note about Jupiter is its remarkably strong magnetosphere. It is 14 times stronger than Earth's, generated by the planet's vast, spinning center of liquid metallic hydrogen. This makes it the strongest magnetosphere of any planet in the solar system, and it is only beaten in intensity by the Sun's own sunspots. There are a couple of reasons why this is really interesting. The first is that magnetospheres channel the solar wind to the planet's poles, which produces magnificent auroras. The second is that the 4 biggest moons of Jupiter, the Galilean moons, are protected from this solar wind because they orbit within the magnetosphere. This implies they do not need their own strong magnetospheres because Jupiter is doing that for them. However, this does not mean they are safe from radiation. Jupiter has a powerful radiation band around it, trapping high-energy particles. This is the same radiation band that has crippled or destroyed electronics on any probe that went through it. The closest large moon to Jupiter, Io, passes right through the heart of this radiation band. It receives 3,600 Roentgen equivalents per day on its surface. For a point of comparison, any human exposed to this much radiation would be dead within 4 hours. It is not the best home away from home. When it comes to the Jovian moons, there are 95 known natural satellites. 57 of them are under 10 kilometers in diameter. But the largest, the Galilean moons, are some of the biggest in the solar system. They are Io, Europa, Ganymede, and Callisto, and they are all interesting in their own right. Ganymede is actually the biggest moon in the solar system and has a greater diameter than that of the planet Mercury. This infrared image, demonstrating the immense size and power of the planet, shows a dot at the bottom. This is the impact scar of an object from space which, if it had hit Earth, could have spelled the end of our planet as we know it. We can be glad Jupiter is there, not only for its beauty, but because in so many ways, it is an asset to our solar system. Uranus, the ice giant, this cold, distant, bluish-gray marble, seems like a desolate waste in the far reaches of the solar system. But, in actuality, there are some fascinating facts about this planet which make it unlike anything else in our cosmic neighborhood. The first unique aspect of Uranus is its name. All the other planets are named after Roman gods: Jupiter, Mars, Venus. Uranus is the exception. It is named after the Greek god of the sky, Uranos. The Latinized version of this word is what we use today. This break in tradition has led to some modern awkwardness, as people stumble over saying the name in a polite way. It even has 2 common ways to pronounce it in English: you're in us and you're in us, as no one has been able to definitively agree on the matter. Uranus is also very special in the way it rotates and orbits. It is the 7th planet from the Sun, the 2nd from last planet in the main sequence. It orbits at an average distance of about 19.2 astronomical units from the Sunday. An astronomical unit is the distance from the Earth to the Sun, which means Uranus is over 19 times farther away from the Sun than our Earth is. This vast distance varies throughout its long year by 1.8 astronomical units, which is the biggest orbital distance difference of any planet. This means its distance from the Sun changes by hundreds of millions of kilometers during its orbit. Being this far away from the Sun means it is freezing cold. It is not just cold, it is the coldest planet in the solar system, even colder than Neptune, which is farther away. Its atmosphere registers temperatures as low as negative 220 degrees Celsius, which is negative 364 degrees Fahrenheit. Its year, the time it takes to complete one orbit, lasts 84 Earth years. When it was first discovered, astronomers attempted to predict its orbit using the known laws of gravity. After some time, however, they realized it had not followed their predictions. The laws of physics are precise, and Uranus was slightly off its calculated path. They concluded that the only reason for this discrepancy was that there must be another planet farther out that had a gravitational influence on it, pulling it slightly. They mathematically predicted where this planet should be, and as a result, Neptune was discovered. Interestingly, this exact same theory surrounds the as-yet undiscovered Planet 9, or Planet X. Some extremely far-out objects in our solar system are not where they should be. According to our models, the prevailing theory suggests this is because of another massive planet that has a gravitational influence on them. The hunt is now on to actually find this planet, using the same logic that revealed Neptune. What is truly interesting about Uranus, however, is its rotation. Most planets rotate like a spinning top on the flat table of the solar system plane, not Uranus. No, Uranus has fallen over, and it is rolling instead. For large portions of its year, you see its axial tilt is 97 degrees. For comparison, Earth's tilt is 23.5 degrees, which gives us our seasons. A tilt of 97 degrees means it is tilted past horizontal. This means its seasons are crazy in comparison to the rest of the planets. During its solstice, the time of year when the sun is highest or lowest in the sky, one hemisphere of the planet faces the sun, and the other is in complete darkness. This isn't just for a day. The summer pole gets 42 years of continuous daylight, while the winter pole gets 42 years of continuous darkness. Imagine an entire hemisphere plunged into a single night that lasts for 4 decades. During this solstice time, only a very narrow strip near the center of the planet, its equator, experiences a rapid day and night cycle. But even there, the sun does only just rise above the horizon before setting again. During its equinox, which is the opposite of a solstice, the planet is oriented side-on to the Sunday. During this period, the entire planet has a more normal, rapid day-night cycle as it spins. Uranus is currently leaving its equinox, having passed it in the year 2007, and is now heading back towards another long, dark solstice. Uranus rotates, meaning its deep interior, or day, once every 17 hours and 14 minutes. Because its surface is not solid, however, some parts of the atmosphere rotate faster than others. This is called differential rotation. Due to high winds, some sections of the clouds can make a full rotation of the planet in only 14 hours. This strange rotation and axial tilt mean it is the only planet in the solar system that gets more energy from the sun at its poles, on average, over its long year, than at its equator. For some reason, though, and this is one of the planet's biggest mysteries, the equator is hotter than at the poles. No one really knows why. It suggests a complex internal heat circulation that our models cannot yet explain. Speculation also exists as to why Uranus rotates the way it does in the first place. Although it is not proven, it is generally accepted that a large, Earth-sized planet, or protoplanet, crashed into Uranus billions of years ago, during the chaotic formation of the solar system. This cataclysmic impact would have been powerful enough to knock its rotation completely on its side, scrambling its internal structure and setting the stage for the bizarre seasons we observe today. How big, exactly, is Uranus? Well, it is the least massive of the giant planets. Its mass is only 14.5 times that of Earth, compared to Neptune, which weighs in at 17 Earth masses. Its diameter, however, is just slightly bigger than Neptune's, measuring 50,700 kilometers across, which is about 4 times more than Earth's. This presents an interesting physical comparison. Uranus is slightly larger than Neptune, but noticeably less massive. This simply means that Neptune is a much denser planet. Its material is packed more tightly together. Because the mass of Uranus is spread out over such a large area, the surface gravity is only slightly less than on Earth, measuring 7.8 meters per second squared, or 0.89 Gs. This means that if you could stand on a platform in its upper atmosphere, you would feel quite comfortable, weighing only about 11% less than you do on Earth. So, what is it made of? This is where the planet gets truly strange. It is believed to have a core just smaller than Earth, made of rocky silicate material. This core is surrounded by a massive mantle, but this mantle is not made of rock. It is made of ices, like water, ammonia, and methane. It is important to understand what ices means in this context. This mantle is, in fact, very hot, reaching temperatures of almost 5,000 degrees Celsius or 9,000 degrees Fahrenheit. It is more like a vast, dense, liquid ocean surrounding the core. Astronomers call these materials ices because they refer to the planet's chemical composition, not its temperature. These materials, water, ammonia, methane, are substances that would be solid ice in the cold, outer reaches of the solar system where Uranus formed. This is why to call Uranus a gas giant is a bit disingenuous. It is certainly not gaseous all the way through, like Jupiter or Saturn are. The atmosphere is, in fact, very insubstantial in comparison, consisting of a total of only 0.5 Earth masses. Most of the mass of Uranus is locked away in this hot, sloshing core and mantle. The atmosphere itself is comprised of mostly helium and hydrogen, and about 2.3% methane. A cloud layer sits on top. It is this relatively small amount of methane gas that gives Uranus its beautiful aquamarine or cyan color. The methane gas in the upper atmosphere is very effective at absorbing the red and orange portions of sunlight, while it scatters and reflects the blue and green light back into space, which is what we see. Very interestingly, some models suggest that the pressure at the base of the mantle on Uranus is enough to break the methane molecules apart. Methane is CH, 4 carbon, 4 hydrogen. The immense pressure, thousands of times greater than on Earth, is thought to squeeze the carbon atoms free from the hydrogen. These carbon atoms then compress into diamonds. These solid diamonds, being denser than the surrounding liquid, would then rain down through the mantle like hailstones. The very base of the mantle could be a layer of liquid diamond or carbon, with solid diamond bergs floating in it. We will fly away from the planet just a little bit now to have a look at its planetary ring system. Uranus, much like the other larger planets in our solar system, has rings. It has 13 known rings, and they are very dark and surprisingly young. Most are not bigger than a few kilometers wide, and they are thought to be only 600 million years old, much, much younger than Uranus itself. This suggests they are not original to the planet, but are likely the result of high-impact collisions with some of its moons in the relatively recent past. They are comprised of extremely small particles, the biggest being only a few kilometers across. They are made of water ice mixed with dark, radiation-processed organics. Their albedo, or reflectivity, does not exceed 2%. In other words, they are darker than wet soil, or as dark as charcoal, making them incredibly difficult to see from Earth. It is unclear why some of the rings are kept so narrow. The usual explanation for such sharp edges is that the rings are kept in by small shepherd moons, whose gravity herds the particles. But this is only the case for one of the rings here. Uranus was discovered to have rings in 1977, before any spacecraft had visited. This was done when astronomers watched the planet perform an occultation of a star, meaning it passed in front of it. They observed that the star dimmed a few times on either side of Uranus, confirming the presence of a ring system. Uranus has only been visited by a spacecraft one time. That was in 1986 by the Voyager 2 probe. This was a very brief flyby. Voyager 2 discovered a lot of the rings and moons of Uranus, giving us our only close-up shots of the faint ring system. When Voyager flew by, it brought the total of known rings to 11. When the Hubble Space Telescope was launched, it also had a look at Uranus, discovering 2 additional rings that had never been seen before. The outermost ring is twice as far away from Uranus as the previously thought outermost ring. And as promised, here is a look at the many moons. Unusually, the moons are named after figures in English literature, primarily from the works of Shakespeare and Alexander Pope. Overall, Uranus has 27 known moons, divided into 3 categories: the 13 inner moons, the 5 major moons, and the 9 irregular moons. The inner moons are connected with the rings of Uranus, and some of them may have provided the material for the rings. The largest of these moons is called Puck, at only 162 kilometers in diameter. It is the only inner moon to be captured in detail by Voyager 2. Interestingly, these inner moons constantly perturb each other, and the system is very unstable. Their orbits are so close together that there is a good chance some of them may collide again in the future. The 5 biggest moons, in order of distance from Uranus, starting on the left, are Miranda, Ariel, Umbriel, Titania, and Oberon. Titania is the largest moon of Uranus and the 8th largest moon in the solar system, at 1,600 kilometers across. As can be seen, these are very dark objects, with Umbriel being the darkest. The exception is Miranda, which is comprised mainly of water ice. The rest are thought to be a mix of water ice and rocky materials. These moons may have differentiated interiors, meaning a core of rocky material with a mantle of ice. Between the core and the mantle, it is possible there could be an ocean layer of liquid water. Interestingly, the axial tilt of these large moons is the same as Uranus. This means that during the solstice, if you were to stand on one of these moons, the sun would only ever move in a circle in the sky, never setting. During this time, only one side of the moon faces the sun, meaning a constant 42-year daytime, followed by a 42-year night. The final 9 known moons of Uranus are its irregular moons. These are not part of the main, orderly family. They are likely to be captured objects passing asteroids or comet-like bodies that strayed too close and were trapped by Uranus's gravity billions of years ago. They orbit much further out than the last of the big moons, Oberon. They vary in size from 20 kilometers to the biggest, Sycorax, which is about 200 kilometers in diameter. Finally, let's explore Uranus's climate and its bizarre magnetosphere. The seasons on Uranus are, as we've noted, quite unique in the solar system due to its exceptional axial tilt. Telescope technology has only allowed us to resolve details on the surface of Uranus for the last few decades. This means it is difficult to be able to say with certainty if there are changes between Uranian years, since 1 year lasts 84 Earth years. What has been observed, however, is that as the planet approaches its solstice, the pole facing the sun brightens, and a distinct cap or collar forms in the clouds. As it moves away from solstice and toward equinox, this pole and its color dim. This brightness is thought to be due to the thickening of methane clouds in that region, but the exact cause is not clear. Seasons also affect storms in the upper atmosphere. Storms are relatively rare on Uranus compared to the other giant planets, but they are thought to be caused by changes in the seasons as the sunlight shifts. With the improvements in telescope technology, we have also been able to observe bands stretching around the planet, much like the other gas giants. However, these bands are mainly visible only in the infrared. This is why the Voyager 2 spacecraft, which viewed the planet primarily in visible light, was only able to show us a mostly featureless, pale blue ball. In these infrared images, you can also see small storms dotted all over the surface. Another unique feature of Uranus is its unusual magnetosphere. Usually, magnetospheres, the magnetic bubble surrounding a planet, originate from the geometric center of the planet and are roughly aligned with its spin. That is not the case with Uranus. First, its magnetic field is not centered. It is offset from the planet's geometric center by as much as 1/3 of the planet's radius. Second, it is not in line with the rotational axis. Instead, it is tilted by 59 degrees. This unusual placement means the magnetosphere is much stronger at the North Pole than at the South Pole. One theory for this is that the liquid diamond ocean we discussed, or the hot, slushy mantle, could deflect the magnetosphere. Another theory is that it is not the core of the planet that produces the magnetosphere at all, but rather the churning, salty, liquid mantle itself. The magnetosphere is, on average, about as strong as Earth's. Because of Uranus's unusual sideways rotation, the magnetotail, the part of the field blown back by the solar wind, corkscrews off for millions of kilometers into space. Look up into a clear night sky with your naked eye. What planets would you see? Technically, you would be able to see Mercury, Venus, Mars, Jupiter, and Saturn at one time or another. You can even see Uranus if you know exactly where to look and have very dark skies, but you would be missing one, Neptune. It is the smallest of the gas giants, or more accurately, ice giants, and also the furthest away, and it is a perplexing place. You would think a planet so far from the sun, so deep in the cold and dark, would not have a dynamic atmosphere. Yet, Neptune exhibits ginormous storm systems and the fastest, most superfast winds in the entire solar system. So why is this planet as interesting as it is? Let's start right at the beginning. Neptune is the only planet found entirely through mathematical prediction. You see, when Uranus was discovered, astronomers began plotting its orbit. They noticed that Uranus was not following their models. The laws of gravity are precise, and Uranus was slightly off its path. From the perturbed orbit of Uranus, a French mathematician named Urbain Le Verrier in 1846 concluded that there must be another undiscovered planet. He predicted exactly where it should be. Remarkably, an astronomer named Johann Gaia was able to find it, only 1 degree away from the predicted point. Triton, Neptune's biggest moon, was discovered just a few days later. But since then, Neptune has been poorly understood. Its extreme distance from Earth and its very small apparent size meant it could not be studied from ground-based telescopes very easily. It was not until 1989, when Voyager 2 arrived for its flyby, that huge amounts of information about the planet became available. Suddenly, we could see what the planet looked like, a deep, rich blue. We confirmed that it had planetary rings and discovered a lot of previously unknown moons. But let's get to today. What do we know about this planet now? Since Pluto's demotion from planet status, Neptune is the 8th and furthest planet from the Sunday. It orbits at 30 astronomical units from the Sun, on average. This means it is 30 times farther than the Earth is from the Sunday. 30 astronomical units, in other words, is 4.5 billion kilometers. From that, you can see why it would take a space probe using current technology, 13 years to reach Neptune. 4.5 billion kilometers is a considerable distance. Because of this long orbit, it takes a huge 165 years to orbit the Sun once. This means that as of 2011, we have only seen one full Neptunian year pass since its discovery. This distance from the Sun means the average temperature in Neptune's atmosphere is very cold, around -201 degrees Celsius or -330 degrees Fahrenheit. Its axial tilt is 28 degrees. This is meaning it is similar to Earth at 23 degrees and Mars at 25 degrees. This means Neptune has seasons similar to Earth, with a crucial difference. These 4 seasons last 40 Earth years each. At this moment in time, the southern hemisphere of Neptune is experiencing its long spring. During this spring, the southern hemisphere receives more sunlight and appears brighter. This increase in brightness is actually quite noticeable, which is strange. You would have thought that because the Sun is 900 times dimmer on Neptune than on Earth, the seasonal change would be minimal, but the planet is clearly responding to the faint sunlight. From that extreme distance, you would think the Sun's faint light wouldn't make much of an impact, but even if it is only a small impact, it makes an impact nonetheless. The increased, though still weak, sunlight levels in the southern hemisphere, now in its decades-long spring, warm it up by about 10 degrees Celsius or 18 degrees Fahrenheit compared to the rest of the planet. This comparably higher temperature is just enough to affect the planet's chemistry. It releases frozen methane ice into the stratosphere, a higher layer of the atmosphere. This methane gas then causes its increased brightness. Elsewhere on the planet, where it is colder, the methane remains frozen and stays deeper in the troposphere, the lowest atmospheric level. Just a quick recap of the layers of a planet. The troposphere is the lowest atmospheric level, where weather happens. It is followed by the stratosphere above it. Above those layers are the mesosphere, the thermosphere, and then the exosphere, which fades into space. If you look at the weather on Neptune, it actually has the fastest wind speed of any planet. Wind speeds have been clocked, blowing westward on the equator, reaching a staggering 2,160 kilometers per hour, or about 1,300 miles per hour. This is nearly a supersonic flow, faster than the speed of sound in Earth's air. And, interestingly, most winds on Neptune travel retrograde, meaning they blow in the opposite direction of the planet's rotation. Atmospheric bands are also formed on the planet, as well as colossal storms. When the Voyager 2 spacecraft passed by the planet in 1989, it saw the Great Dark Spot. This was a storm about the size of the planet Earth, churning through Neptune's blue atmosphere. Voyager also saw a smaller storm, known as the Small Dark Spot, located south of its big sibling. As Voyager 2 approached Neptune, this smaller storm visibly changed in shade from dark to light. When the Hubble Space Telescope was launched, astronomers were curious to see the fate of these storms, to see if they were a permanent feature like Jupiter's Great Red Spot. But when Hubble was pointed at Neptune in 1994, these storms had completely disappeared, and storms have come and gone ever since. Giant, bright, high-altitude clouds of methane ice also come and go. But why, then, doesn't Uranus, which is very similar in composition and size to Neptune, also have such a blustery, active atmosphere? Don't get me wrong, wind speeds on Uranus are fast, too. but they do not compete with Neptune's, reaching only about 900 kilometers per hour. Can all of this activity on Neptune only be due to interactions with the faint sun and its long seasons? Something else must be at play here to explain the extremes in weather. The answer may lie deep beneath Neptune's surface. I mentioned that Neptune is the furthest planet from the Sun, so you would have thought it is also the coldest. But actually, Uranus is the coldest planet in our solar system. Neptune is slightly warmer than it should be. It radiates heat from within, whereas Uranus radiates hardly any excess heat at all. This could be because that large, Earth-sized body that is thought to have crashed into Uranus billions of years ago not only knocked it on its side, but also depleted all of its primordial heat, allowing it to escape into space. Neptune, which avoided such a cataclysm, retained its internal heat. Astronomers now theorize that the more active weather on Neptune might be due, in part, to this higher internal heat, which provides the energy to drive its powerful winds. What is Neptune actually made of then? Its internal structure and atmosphere are thought to be very similar to Uranus. Its atmosphere is composed of mainly 80% hydrogen and then 19% helium, with very small amounts of methane. It is this methane, just like on Uranus, that gives Neptune its blue color by absorbing red light. However, it is a much darker, richer shade of blue compared to Uranus's pale cyan. The reason for this deeper blue is unknown, suggesting another unidentified chemical is at work. Again, like Uranus, there is a vast liquid mantle of water, ammonia, and methane ices surrounding the core. And where the core and the mantle meet, the pressure is so great that the methane may break apart, and diamonds are formed under the pressure. This is likely not diamonds as you or I know them, but there could be a liquid carbon ocean with solid diamond bergs floating in it, and diamonds raining down through the mantle like hailstones. This is just a theory though, as technology has only recently started to recreate such pressures. Around the core of Neptune, the pressure is thought to be 7 million bar, or 700 gigapascals. This is about 7 million times the pressure of Earth's atmosphere at the surface. Even the two ice giants' magnetospheres share similarities. Neptune's magnetic field is offset, just like that of Uranus. It is tilted 47 degrees relative to its rotational axis, and is offset from the planet's center. When Voyager 2 discovered this about Uranus, the first theory was that it had something to do with its unusual axial tilt. But then it found the same thing out about Neptune, which has a more normal, Earth-like axial tilt. So, the current theory is that the magnetic field is either not generated in the core at all, but rather by the electrically conducting liquid icy mantle, or that the mantle itself deflects the magnetic field from the core, which gives it this weird offset. Every planet in the solar system has not actually got a perfectly aligned magnetic field. Even Earth's magnetic north is different from where the true North Pole actually is, but it is only Uranus and Neptune that have such a radically tilted magnetosphere. Auroras do exist on Neptune too, but they are different from what you might expect. They are extremely faint, due to the particles from the sun not getting as charged at that extreme distance. And because of the strange direction of the magnetosphere, they are not simple rings at the poles. They are complex and smeared across the planet. Another difference with the auroras on Neptune is their location. Unlike the familiar rings of light seen at the poles of Earth or Jupiter, Neptune's faint auroral arcs are not only found around the poles. Because of the planet's wildly tilted and offset magnetic field, these energetic displays are smeared out, appearing more around the mid-latitudes of the planet. Zooming out from Neptune a bit, we come to its ring system. Like all the other giant planets, Neptune does have rings, although they are extremely faint and difficult to detect. They are not as dense as Saturn's, and they are made of extremely dark material, likely processed by radiation. If you have these rings against the black backdrop of space, and also have them be this far away from the sun, where illumination is minimal, they become nearly invisible. There are 5 known rings in all, and they are named after people involved in the discovery and research of Neptune. The innermost is the Gale ring, which is very faint and very wide, stretching about 2,000 kilometers across. Next is the first of the bright rings, the Leverrier ring. Although it is considered bright, this is relative. It is still incredibly dark and is only 113 kilometers wide. Connected to it is the Lassell ring, a very faint, broad band of dust, about 4,000 kilometers across. On the outer edge of this ring is the Arago ring, which is slightly brighter than the Lassell ring and measures less than 100 kilometers wide. Lastly is the outermost and the most researched ring, the Adams ring. It is very narrow, only about 35 kilometers wide, but it is one of the brightest. This ring is particularly interesting because it is slightly inclined, not perfectly flat with the equator, but its most bizarre feature is that it contains several bright arcs. These arcs are sections of the ring that are much denser, where material has clumped and clustered up. They have been quite stable since they were first discovered in the 1980s. This is a deep mystery, because usually, planetary rings are uniform all the way around. The laws of physics dictate that the material should spread out evenly over time. The fact that these arcs are held in place suggests something. Perhaps a small, unseen shepherd moon is gravitationally corralling them, but the precise reason for this clumping is currently unknown. Lastly, I want to talk about the moons. Neptune has 14 known moons, which are named after minor water deities in Greek mythology. The most famous, and the largest by far, is the moon Triton. This moon actually contains most of the mass of all of Neptune's moons put together. It is a visually stunning world, with amazing patterns and a distinct burnt orange color on its surface, thought to be from nitrogen ice reacting with faint sunlight. What is most interesting about Triton, from a scientific standpoint, is the fact that it orbits in retrograde, meaning it orbits backwards against the direction of Neptune's rotation. It also orbits at a sharp inclination, or tilt, to Neptune's equator. These two facts strongly imply it is probably a captured object. It is not something that was formed alongside the planet in the same disk of material. Instead, Triton was likely a dwarf planet, similar to Pluto, that formed elsewhere in the Kuiper belt and then strayed too close to Neptune, where it was captured by the planet's immense gravity. This capture event would have been chaotic. Scientists theorize that Triton might be the cause of Neptune's rings. As it was captured, its large gravity would have severely disrupted the orbits of any original, smaller moons that had formed with Neptune, possibly causing them to collide and break up into the rubble that now forms the ring system. Triton is even bigger than the dwarf planet Pluto, and also has a thin, tenuous atmosphere made of nitrogen. The Voyager 2 spacecraft even saw faint clouds and active geysers of nitrogen ice erupting from its surface during its flyby. The next biggest moon is Proteus, which is a little irregular in its shape. Normally, we only see this lumpy, potato-like shape on smaller objects like asteroids. But Proteus is actually quite large, at 400 kilometers across. It is bigger than the spherical moon of Saturn, Mimas. The fact that Mimas is a sphere and Proteus is not is explained by past collisions. Proteus, appears to have been hit by objects so large that they left massive craters, nearly shattering the moon and preventing it from ever pulling itself into a round, spherical shape. The inner regular moons orbit around the rings, with some acting as the shepherd moons that help maintain the ring edges. The outer, irregular moons are all likely captured moons, just like Triton, but much smaller. Some of these irregular moons orbit prograde with the planet, and others orbit retrograde against it. The outermost moons of Neptune are Psamathe and Neso, and they are the furthest out satellites of any planet that we know of to date. They take a massive 25 years to orbit Neptune only once. This is possible only because Neptune has a very large Hill sphere. The Hill sphere is the region of space around a planet where its own gravity is the dominant force, overcoming the gravity of the Sunday. Because Neptune is already so far from the Sun's gravity has less of an influence around Neptune than it does around a planet like Jupiter, allowing Neptune to hold onto these very distant moons.